guys, am I okay on the mic? Yes. Maybe I'll take it out. Welcome to tonight's event. We have a pretty large crowd here. I'm excited, and I hope you are too. From the looks of what I've been hearing and seeing, I think everyone's just as excited as I am. I wanted to thank Park for making this event possible. As you all know, and by your attendance here tonight, this is a pretty relevant and timely topic that everyone is interested in, and there's a lot to be learned. Governor Brown just passed SB 4, which is going to allow fracking in the state of California, and it is with very strict regulation, but there are still a lot of concerns that we all have, and George King is here with us tonight to help educate us on what we should really be thinking about as opposed to maybe some of the red herrings that the media has been focusing on. So we're going to get into some technical nitty-gritty, and I think we'll all enjoy it. George is with us here from Houston, my hometown as well. He grew up in Oklahoma, but he's now settled down in Houston with his family. I would have to say he's probably luckier than most of us in that both of his children and all his grandkids live within a 5-mile radius of him. And they vacation down in Tiki Island. Yes, that is a real place. And it's withstood the hurricanes of the Gulf. George has, I'm not gonna rattle off his list of accomplishments because it's in the program. He has many. He gives about 25 to 30 presentations a year. He's highly sought after. He's an expert in the field. So much so that investors use his technical checklist to determine interest rates that borrowers get when they want to invest in fracking and wells. I think that's pretty impressive. So without further ado, Mr. George King.
Thank you. First off, thank you very much for having me here tonight. For those of you who expect a hard sell on fracturing, you won't get it. I've been in fracturing since 1971, was hired into the petroleum industry by a man whose name is on the main hydraulic fracturing patent that was issued in 1952 and was part of the crew that pumped the very first frac. So I've grown up in my professional career of 43 years now around hydraulic fracturing. I've seen it succeed a great many times. I've seen it fail spectacularly. And with Amoco and later with BP, who bought Amoco, one of my tasks was doing post-mortems on failed wells. So believe me, I do know where they leak. And we're going to talk about some of that tonight, both the high points and the low points. At the end of it, I'm going to show you, if I was a regulator, here's what I'd be most interested in. And I think that will be a very good place to actually start the conversation. Now, these are the things that I'm going to try to address as I go through here. We're going to talk a little bit about how it works, what it is. And believe me, it's not an explosive force down hole. A hydraulic fracture grows at about a foot or two a second as you pump fluid into the well. I've actually got downhole pictures of a hydraulic fracture starting. Talk about the chemicals. I don't care if the service vendor does not want to tell me the list of chemicals. We found a way to make sure that what they bring onto our location doesn't bring any chemicals there that we don't want. I'll share that with you. We recycle a lot of produced water. In West Texas and Oklahoma, our main objective areas in the United States, almost all of our jobs have a minimum of 25 to 40% recycled water in it, and some of them are 100% recycled. Tell you how that you can do that and what it takes to do it. And methane escaping into the atmosphere, some very simple solutions on that. Can fracturing cause earthquakes? And fracturing doesn't cause earthquakes that you can sense at the surface, but watch the injection wells. We're going to cover that. And then how do you focus on the real risks and how does that shift the debate? Because there's a lot of what are really green herrings, most of them raised by the environmental movement, which has some very good points, and we work with them. We actually work with several of the environmental groups. But here's what we're going to talk about during this evening. First off, shales of North America. The most information that you can get from this is there are a whole bunch of shales out there, and no two shales are alike. But they do have a huge amount of primarily gas. There are several that do have liquids, but I'll tell you right now, liquids are going to be much more difficult to get out of shales than is the gas. These are low permeability rocks. There are about 10 producing shales that are economical in North America right now. There's a lot that are not economical. And so this breaks down into what does it take to make it flow? Can't go into all of those details, but I will tell you it is very, very sensitive to economics. Now, where are we in terms of how much shale gas is actually being used? We're in about this area right here, and about 30-35% is our target of what we're heading towards. We're maybe at 20% right now. We've got a lot of shale gas wells that still haven't been fully stimulated. There's a lot of gas out there. 100-year supply at current rates, that's pretty conservative. Probably got more than that. I will say that we've been so successful that we're a victim of our own success. We started when gas was $10 an MCF, and now it's a little less than $4 in most cases. That's not the direction we wanted it to go, but that's the way it happened. Now, on fracturing, we drill about 10,000 to 20,000 wells a year in the U.S. depending upon the activity level that we get into. Horizontal wells are rapidly overtaking and in some areas have completely displaced the well type from vertical wells that had one frac in them in one zone to horizontal wells which have replaced 5 to as many as 20 vertical wells because you can whip that out, go a long ways out, and put several fracs along its length. That is a specialty to very low permeability formations. Permeability meaning the ability to flow. And you've got to use fracturing to enhance that ability. These are reservoirs, shales, low permeability oils, etc., that would not flow without the assistance of fracturing. Fracturing from the late 40s and 50s when it became popular up to about the middle of the 90s to the late 90s was a production accelerator. Those formations that we were fracturing then would flow that oil. We were just making it get quicker. All right, with shales, there's no secrets on all these shales. We've been drilling through them for years. We knew where they all were. It's just how to make them produce. Shales at that point need to be fractured just to flow. It doesn't accelerate it, it makes it possible. Now, of all the wells that are drilled and all the fracs that are done, basically what we're looking at is about 50% of those fracs are done by the top 50 U.S. oil and gas producing companies. The other 50% are done by somewhere between 2,000 and 3,000 small companies that may have 1 to 10 wells. All right, some of them don't even have an engineer on staff. They don't generally design their own frac treatments. That's done by the service vendor. But if you don't have enough technology in place, that makes it difficult to do this thing correctly. I'm not saying it can't be done. I'm saying everybody needs to be on the same playing field in order to do this right. There's a lot of things that we go through from project analysis through development drilling, and it's a long-term step. I'll show you the time and the money involved in that in another slide here in just a minute. That goes down into about maybe as many as 25 to 50 pumping companies. There's over 700 frac fleets in North America, U.S. and Canada. the most in any part of the world. Europe has like 7. South America has half a dozen to maybe 12. So the U.S. is the center of fracturing. That's where our experience comes from. We did 1 million fracks between 1947 and the mid-1990s. That's a pretty good length of time right in there. That was 1 million fracks, and it was typically 1 frack on a well. Now, since 1995, when horizontal wells really started coming on and we started doing multiple fracks down the length of this horizontal, we've done 1 million fracks since 1995 to now. All right, because we drilled a lot of horizontal wells, and every one of those horizontal wells has anywhere from 10 to as many as 52 fracks down the length of this thing. The record is in Bakken at 52 fracks right now. Now, those are the people that do the work, but you may have as many as 10 and upwards of 20 different companies involved in the well development of any particular area. A lot of employment, a lot of activity out there. It's a spike in the activity, and then it comes down and you're operating it. The jobs don't all go away. It switches from the frantic level of pumping this, which is a lot of the problems that we have with fracturing, is this rush to get into it, and the production over time. We'll talk about that. This is how the thing goes together. This is well development in a nutshell. We start out leasing the land. We make seismic assessments, actually lease the land as part of that. Those two go together. The site preparation, I have the time up here from 2 to 4 weeks to 1 to 2 weeks here. The drilling takes about 2 to 4 weeks. The fracturing, the completions and fracturing, we think of this, fracturing. Each fracturing job is only 2 hours to about 3 hours long. That's not really a big overpressure issue. Where is the issue? It's in the 4 to 20 plus years that we're going to operate that well. You better get your construction on that well right, because that's where it's going to be tested. Those are the things we need to look for. Some basic prices going out here and some estimates of what Barnett to Eagleford wells cost. The deeper the well, the higher pressure of the well, the higher the temperature of the well, generally the more the cost on this thing. Fracturing was, in vertical wells where you had 1 frac, it was 25-30% of the job, and drilling was king. It was spending 65 to 75% of the money. Now, in shales, drilling may spend 25% of the money or 30% of the money, and the rest of it is fracturing. And the drillers are a little jealous. Now, when you look at all that money being spent, it looks like a lot, but there's a lot of activity going on there. And that's where economics comes in. You would think oil companies would be just throwing money everywhere. It just looks that way. All right? Now, we have a lot of statements out there in the media. And basically, you got one side saying it's terrible, and you got the other side saying it's wonderful. Well, I'm kind of in the middle. It's good if you're willing to do it right. And I do a lot of teaching, I do a lot of speaking, and what I tell operators is either do it right or get out, because you're really screwing it up for the rest of us. Everybody has got to do this correctly to make it work for the entire mass of companies that are out there. We need to be very careful what we're doing. So these are the things that we look at. You know, there's some truth on both sides. If you want to really know what's going on, just follow the money and the agenda of the position supporters. Now, we continually work with some of the better environmental groups, the Endocrine Disruption Network. We work with the Environmental Defense Fund. We work with several others that are willing to work with us to help make the process better. And I'm not going to tell you that every formation can be fractured. I don't think they can, safely. There's areas that I wouldn't go into, and I've walked away from several. And I'll share some of that with you as we go on. Now, this is beautiful spot in Texas. It doesn't all look like this. This is actually 2 wells. The wellheads are here and here. They look close together. Actually, they go out and then they'll go to any direction you want to go. We have them on a small area of a pad. We clear that pad off. We have to build that up to where it will stand the weight of the trucks and the other heavy equipment and the tanks that we put on it. And these pads can be anywhere from about 2.5 acres up to maybe 3 or 4 acres. I'll show you a little bit larger pad, but I'll also show you a way to reduce the footprint. You've got your pumping units, you've got your blender trucks, you've got your water and sand storage areas, but you've got it for 2. And there's actually 2 frac fleets here that are pumping jobs at exactly the same time. And it's a technology that was developed in the Monterey Shale. And so this is a developing technology series. Now, this is what a fracture looks like downhole. For those of you who think we can't see downhole, we really can. These are downhole television cameras. This camera was actually developed in the 1960s by Amoco Research. I got to work on this project a little bit in the 70s. But these are hydraulic fractures, and this is a scale of 1.5 inches on this whole thing here. So these fractures are about 1/4 inch wide. They're not huge things. And they grow upwards. The height is limited by the amount of leak off, by the stresses in the rock, by natural fracture barriers, and by the depth of your pocketbook as to how much fluid that you can afford and how long that you can pump it. And if you look at the economics on something like this, you'll find that there is a set limit to the benefit that you can get versus the money you can spend. And it changes from well to well and from formation to formation. The fluids we use have changed a little bit over time. We started out in this industry, the first fracs back in the early 1950s, people really believed that water would hurt a formation, and so they were pumping oil. And then they were pumping, believe it or not, gelled gasoline. Napalm, same formula. They pumped that. Toasted a few trucks, but they pumped it. I'm glad I wasn't around for that one. All right, now, what they went to finally was gelled water at the end of the 50s through the 60s. Slick water was actually pumped in the 50s, didn't do much, wasn't good for the formations, the porous sandstones and the better carbonates that we were fracking. And so most of it was gelled fracs. Well, slick water, and what slick water is, that's salt or fresh water, and if you give me the choice, I'll use salt water because it's easier on the formation. And that will have a friction reducer, polyacrylamide, and a biocide. We use glutaraldehyde. And low concentrations of those total additives, the risk level there is actually very low, but you can have quite a bit of chemical if you hauled it all out to location at one time, as some people suspect we do. You'd have a lot of chemical on location at one time. As we pump this, we use small volumes of it, and you bring it out a small volume at a time. But when I analyze the real risk factors, the biggest risk factor wasn't fracturing. That was a distant, way down the line risk. The biggest risk factor was hauling chemical with traffic accidents thrown in, rollovers, etc. It isn't from pollution from down the well coming up, it's from spills going into the groundwater. Okay, more about that as we go along. Now, since that time, we get into oil, we need to carry more proppant. You know, we open those fractures up that I showed you, but once you release the pressure, they'll come back together. So we've got to put sand or other types of proppant in there, and that's where we went back and used some gel. So we'll start off with a slick water and then go to a little bit of a gel later on to carry the proppant. The slick water penetrates the shale. And this is a naturally fractured shale. Think of it this way. If I've got to split a log, I got two choices here. I can use a big steel hammer and just hit the end of that thing forever. It's not going to split. But if I take that thing and wedge it to a point, drive it in, you can get a nice split in a log. All right, same thing is true in naturally fractured formation. You've got all these little natural fractures, most of them closed. Put a water in there, low viscosity water, it penetrates those, you raise the pressure and it breaks it apart. That's a technique that's been used in stone quarrying since the before current era time period. So we do that with water. Now, what are the chemicals? Notice here, and this I think absolutely needs to be, they are the chemical abstracting service number on every one of these. I can tell what I have in there. I know exactly what it is. Every one of them needs to be in frac focus. That should be part of any regulation. And it is in most states right now. Normally we pump a minimum of additives, and if service vendor doesn't want to tell Apache what they're pumping, we don't want the recipe. We don't want the exact formulation. That's what's really secret. The additives aren't. But they've got to send us that CAS number of every material that will be in there. We look down the list. We don't like it, we don't pump it. That's the control that an operator has, and that's control any operator can have. You can stop endocrine disruptors, carcinogens, the super toxic, the non-biodegradable. You can stop that. What you do is you specify design for the environment chemicals that are on the list that's put out by EPA. You can qualify chemicals for that list, or gold band chemicals from the North Sea. That's been studied for years. That's a simple problem to solve. You don't have to know the recipe. You want to know the components that's in there. All right, most of these, and we only use 2 to 3 additives in a total mix of a frac job. I know that there are 700 and some additives out there according to Gasland. Yeah, there are, but we just don't pump them. So it's an easy way to actually get around this. The other thing is science matters here. The first thing people learned is that the shales are a tough place for the old wildcatters, the people that would go out and drill a well hoping it would come in. We call those the poke and hope crowd. All right? They didn't do real well in shale because here is the heart of the Barnett Shale, the first really successful shale development. The green areas are the best wells. Well, that's only about 25% of the entire core. There's areas out here in red that no company ever got to make a commercial well in. All right? So this is the problem that we get into. Where is the best place? Because if you drill a bunch of wells in there, you're increasing the risk of a problem without getting production. Science matters. Find out where to drill, get your technology sharpened, make this thing work. Technology is not resident in the pig iron, the color of the pig iron, it's on location. Technology is resident in people. And it's the people that have made shales possible. You will notice if you look at the first developers of every shale in North America, not one has been opened by a major or a super major. Every one of them has been opened by a handful of independent oil companies with very, very sharp people and techniques. That makes a difference. Now, what changed the game here? It was the incorporation of the horizontal well, which has been around for 50 or 60 years, and fracturing, which has been around for about 60 years. Now, put those two together, and suddenly I've reduced the well count, I've reduced my cost, and I cover a huge amount more area than I was ever able to cover from a smaller footprint at the surface. Less water penetration, less water sand penetration. This makes sense. All right, first multi-fractured well was in 1952. The first multi-fractured deviated well or horizontal well was in 1974, but it didn't become popular until the late 90s. First time it was used in shale was 1988 by the Department of Energy in a grant. Okay, but you look at this and you say, okay, what's the difference? The difference is to get this much area covered by conventional, I'd have to drill 6 wells or 7 in there. Now, let's take it a step further. Here's an interesting one. This is Apache L34 pad, Horn River, British Columbia. The Forestry Department, which is your main control there, says you can have 6 acres and 6 acres only and don't cut any more trees than that. Yes, sir. And so we put 12 wells here, right on, you can see them in the little yellow boxes right in the center of the picture. That's 12 little well houses right there. Look at all the trucks that are backed up there. Those are the pump trucks. Those are there for 4 months, from Christmas through the middle of April. And they're fracking 24 hours a day. The first year we were up there, British Columbia said, yeah, you can use the lake waters as long as you don't draw it down more than 8 inches. Okay. They said, but the next year, we don't want you using the lake water. So we found a saltwater zone, and we switched from freshwater to 95% of the volume we pumped the next year in this particular pad was salt water that wasn't good for any other purpose. Couldn't even run it through an RO unit. Guess what? We got better wells, and it was about the same price, probably a little bit cheaper. So can it work? Yes. That reduced the footprint over vertical wells over 93%. Can be done right. Now, that's for gas. It's harder to do it with oil because you have to have pumps in there. And we still don't have really, really good pumps for horizontal wells that don't produce very, very large volumes of fluid. Now, where do the natural fractures stop? There's 4 controls over that, from the formation barriers to leak off itself. I mean, I can be pumping at 100 barrels per minute. Barrel is 42 gallons, so that's 4,200 gallons of water per minute going down that well. Those pumps are screaming. All right. What keeps the frac from growing all over the place? As you get more and more of that frac open with a high pressure down there, the liquid is leaking off along the fissures, fractures, porosity. And at 100 barrels per minute, 250,000 square feet only requires 0.3 ounces per square inch. And the fracture stops growing due to leak off control. You're not going to frac out a zone. We're not going to frac up to fresh water in a deep well. And I'll say deep, more than 2,000 feet. If I frac a well less than 2,000 feet, I'm extremely nervous because I don't have that big safety margin there. Now, how do we know that? How do we know where the fracs go? This is microseismic. It is an outgrowth, and basically it's taking earthquake measuring technology and earthquake positioning technology and saying, okay, this is where your fracture goes. Each one of those little points during several fracs along those horizontals is a little microseism. And that energy is like taking a jug of milk, holding it at chest high, and dropping it on the floor. Same energy. Mark Zoback down at Stanford is the one that came up with that analogy. And he studied earthquakes. All right? It's not a lot of energy compared to an earthquake. In fact, it's a -2 moment magnitude, so 1 billion times less than a 6.0 earthquake. You all know earthquakes better than I ever will. I haven't felt one in Oklahoma, in Texas. We used to have our house in Oklahoma built on bedrock, And of course, that's not too far from that New Madrid fault. And we had a chandelier in the bedroom, and I'm not going into why we had a chandelier, but we did have a chandelier in the bedroom. And you could be laying there watching TV with that light on, and all of a sudden you'd see that just chandelier just start vibrating, and then it would do its little swing through the deal. So yeah, we did have some earthquakes up there. These little microseisms are triangulated by recording device or listening devices here, and they're really pretty good. They're plus or minus about 50 feet in terms of accuracy of position, but they tell you about where that thing is. And they're very, very useful in the first few jobs in an area that are pumped to help optimize where that frac is going and what I need to change. Let's face it, if a frac goes out of zone, I'm losing money. There's no point in that. And so, again, it's about economics. This is a pretty good little presentation here. They took, and they meaning Pinnacle, this was done by a couple of friends of mine, they took 2,300 jobs done in the Barnett, 2,300 frac jobs. They plotted the very top point of every frac. And there's a few that go up higher than you think they would. It's probably not even hydraulically connected, but we'll give it worst possible case. The bottom of the water is in blue, and that goes, there's some of it as much as 1,200, 1,300 feet deep, but each one of those major divisions is 1,000 feet. Do you get close to water with a deep well? Not even close. That's our safety factor. You get down here and start dealing around at a well that's 2,000 feet or less deep, I get nervous. I'm going to pump a little bitty frac if I pump a frac at all. In fact, I haven't pumped a frac less than 2,000. Apache doesn't even have one, a well less than that. Most of our wells are about 3,500 and deeper. So that's, again, a safety factor that really keeps us from getting into trouble. I said that it was low permeability. Let me give you an illustration. All right, there are your Mid-East reservoirs out there, and every division coming along that line is an order of magnitude. Here is the concrete beneath your feet. Here's shale. Okay? This runs way down, and if you don't have enough surface area of contact with shale, you will not make a successful well. That's one of the lessons that had to be learned. Now, does it decline quick? Yes, it does. But it's an unusual decline. It's what we call flush production. Any naturally fractured formation that you drill and try to produce will give you a big shot of fluid to start with, and then it'll fall off reasonably fast. Is this a problem? Not when I've got 100 or so wells that are consistently making this volume of gas, and what happened right here? That's your flush production. That volume of gas probably paid for my well in the first 6 months. Again, this is something that is characteristic of the shales and any naturally fractured formation. So let's get into the potential for groundwater pollution. Talk about that for a second. A lot of screaming about fracs are polluting. And I started digging. And here's what I found. This is an EPA assessment, and this was the top 10 contaminant sources from 42 states, tribes, and U.S. territories that were reporting. The year was 1999. They published it in 2000. Oil and gas is not on the top 20. The shallow injection wells, when you check that out, that's the class 1 injection wells where they're injecting pickling brine and a few of those other things that are manufacturing derivatives. That wasn't us. But the rest of this, and really you don't, if you're operating on a well, please don't read this list, because basically what you're going to find with is the biggest pollution source out there. Gasoline and gasoline and diesel from your neighborhood filling station, your neighbor's septic system, and agriculture. Those are the huge ones. And you will see this in groundwater. These are your big pollution sources. Now, that was 2000. Let's take another look. And I had the benefit of being in Texas here. Parts of Texas are extremely nice. But we've drilled over 1 million wells. We've fracked over 500,000 wells. And half of all drilling in the United States now is happening in Texas. All right? We've got 29 aquifers, major and minor. They cover 90-some% of the state. Every one of the wells that we have drilled has gone through an aquifer. 1 million wells. And we're drilling probably 10,000 a year. All right? Now, when you look at that, and Texas is the number 2 total withdrawal of groundwater after California, 80% to, well, it's actually 85% going to agriculture and municipalities. If you had toxins in that water coming from the oil industry, you're going to know it pretty quick. You don't see them. I'm not saying they're not there. We're not doing this thing perfectly, but let's look at what is there. And this is, I went back and pulled the records from the TCEQ, the Texas Commission on Environmental Quality, the Railroad Commission, the Groundwater Protection Committee, etc. These are the bad ones. And if you memory flips back to that EPA slides, there are a lot of the exact same thing. You had a lot of gasoline and diesel still coming in from those old steel tanks. Notice that the control problems, or the controls that they've got out there, are doing a nice job of reducing that. That's great. But there's a lot of manufacturing stuff in there that comes on down. Again, oil and gas wells aren't on the list of the top 20, but here's where I found them. All right, most of the complaints are surface. Surface facilities, there are pipelines, and this is underground petroleum storage tank. Again, gasoline and diesel, but these are the ones I was interested in. Surface facilities, pipelines, and when I'm talking about this, that's gas plants, tank batteries, truck loading terminals, etc. Surface pollution that's going down. It's not coming up, it's going down. Now, gas and oil wells are on the bottom right there. You'd find just 1 or 2 in almost every year. What is it? It's bad cement. Or it's leaking connections. You think cement is the number 1 cause of problems out there? It's not. It's leaking pipe connections. I studied reports on 650,000 wells to write this document. Now, take a step back and let's look at this historically. And when you do that, you're seeing orders of magnitude drop in the potential for pollution from the first gas well, 1825, William H. Hart gas well, Fredonia, New York. It hit gas at 28 feet. Drake's well, 1859. He hit flowable oil at 69.5 feet. He followed the oil springs down Oil Creek to a town just the other side of Oil City to drill his first well. Now, and they're amazed at they have oil and gas in their water wells now? Yeah, okay, there is some relationship there, but they've coexisted for a long time. But this was the era from 1830 to 1916. This is early 1900s where it started drilling in Texas. Before that, Pennsylvania and Ohio were the oil capital of the world. Guess what they didn't have in any of those wells before 1903? Cement. They drilled a hole, they drove the pipe into place, and they produced it. Whatever came up on the outside of the pipe came up on the outside of the pipe. You got a big batch of oil spilling all over the place, you burned it off. That's pollution. Severe pollution back then. All right, cable tool drilling. Doesn't have a hole full of fluid, doesn't have pressure control on the formation. That's the gushers that you saw coming over the old wooden derricks years and years, the old pictures. Then rotary drilling came in. That jumped it down. Blowout preventers were invented. That knocked it down. You got a lot of things starting to lower this potential for pollution in these eras. Even fracturing helped because that reduced the number of wells they had to drill, because to that time they were drilling a well, and if it didn't produce, okay, it didn't produce, they went on to the next well. Sometimes they would plug it, most times they wouldn't. Biggest problem, none of those old wells that weren't plugged or cemented. I am tickled to death that Pennsylvania and Ohio led Texas for 50 years in terms of oil production, because when they started in Texas, they actually started using cement. In Pennsylvania, one of the reasons I wouldn't want to operate there is they have probably over 100,000 old wells, uncemented, unplugged, and they don't even know where they are. So when people start drilling and they air drill up there, which is a problem, they pressure up those water sands, all of a sudden it's got oxygen flowing into it. Any methane that was a pocket in there is pushed into somebody's water well. And by the way, all that oxygen in a water zone really increases the amount of aerobic bacteria that's growing. And so people's water turn yellow, it stinks, and it's got gas, and your garden hose will burn. That happens a lot in Pennsylvania. Of course, it's happened for 200 years, but it still happens a lot. A lot of these things have really lowered it. One of the biggest was getting good regulations. We push for good regulations. State regulations is what we prefer, because those are the people who know the location, know the localities, and they more than likely have trained people who used to work in the industry or have worked beside the industry. They know what's going on in the well, and it's really hard to fool them. That's what I want to see out there. I want to see experienced people. Now, how much water do you use? 3 to 4 million for all of the fracks in one well, not just one frack, all of the fracks in one well. Okay, so you're looking at, say, 5 million. Well, what's 5 million gallons? Well, a coal plant uses 5 million gallons for heating, cooling, all of this, for cooling and scrubbing and all of this. It uses it in 11 hours. A nuke plant uses it in 6 hours. But there's a difference between just using it and consuming it, because you don't want to flow anything that comes out of an oil well or a gas well. Don't flow that into a river. Pennsylvania would allow it. Up till about 2009, somewhere around in there, 2010, they had to change the rules. But they had these little bitty fracks, so it really wasn't much of a problem, and acid mine drainage was a big problem, so that diluted it a little bit. Well, what they were doing in Pennsylvania in 2008, they would put you in jail for in Texas or California. Most western states had much tougher laws, and it needs to be. How much water do you get back? Well, that's 30 to 50%. Some of these are 5 to 15%. Shales are undersaturated to water. It's like, flowing water into a dry sponge. Spilling paint on an old weathered board, it's going to soak in. And it holds it. Doesn't come back very easy. In fact, if it comes back, it'll be fresh water because it'll vaporize out and be carried out with the gas. So it doesn't see a lot of that coming back, but that volume of water, that's typically about 1% of the total in Texas, about 1.6% in 2010. However, that's misleading, because in certain areas, it was 5%. In one little area, it was 20% of the water supply. That's when we started looking at this and saying, this is not a sustainable use of groundwater. We're pulling it out way faster than it can recharge. In almost every aquifer, we're doing that. Here, there, doesn't matter, we're doing it. Surface water is a better one. Recycling water is much better. And that's what we have to look towards. All right, how much water, when does the water flow back? That water starts flowing back at a very high rate, drops like a stone, and within 15 days you are down to a background rate that may be a tenth or even 5% of what it started at. And it will come on down from there. Shales are undersaturated to water. They don't like to give it up. And after a while, if you're still flowing salt water out of that shale well, you've probably fracked out a zone. Work on your technology. That's a key piece here. Keep that frack in zone. So, is it a major factor? You'll get the flowback, which might be 43% of everything that's produced out of that shale well, you get it in 15 days. The rest of it may come over 10 to 20 years. That's a minor amount to transport. And generally, you can find a way to dispose of that either back into an existing depleted oil zone or use it in a water flood. There's ways to do that. You can track it by looking at the ion ratios, the ions themselves. So there's ways to see this. There are a lot of technologies that are still being developed as we go along. The other piece that I like to bring out is people will see oil and gas and say, oh, well, that's terrible. We've got oil in the Santa Barbara Channel, those terrible oil companies. Well, the world's largest seep is the Coal Point Seep in the Santa Barbara Channel. Flows about 2,000 gallons now, not barrels, gallons of oil a day and about 2 million standard cubic feet of gas a day. It used to flow a lot more than that, but they drilled some wells from onshore out into the feeder of that seep, and they've reduced that about 50%. So it's being fed from a deeper reservoir. But you still see a lot of those seeps. On the North American continent, they have 1,100 identified seeps. I've heard in California they have over 1,000. In the Gulf of Mexico, they've got 200 to 300 oil seeps. You've got gas seeps all over the place. What's your most famous onshore oil seep in the U.S.? The La Brea tar pits, the Kitteridge tar pits. Down in Trinidad, you've got that Trinidad oil lake down there. You've got a lot of this natural product, this oil and gas coming up, a little bit of it at a time. Hey, the bugs eat it. It oxidizes if it's gas. The bugs eat it if it's oil. It isn't really that big of a problem. Your localized flora and fauna adjust to that. It's when you get a Macondo that it really screws things up. So those are the things we've got to watch. Now, this area that I've drawn out here, this is your seep area in black. You can see the gray area over there are your soil seep areas that are high with methane. Guess where your oil and gas wells are? The red are the highest density of oil and gas wells. You know, it's just right through the U.S. It follows it. This was the earliest prospecting tool we had was seeps, and we drilled those seeps. That's what Drake used. That's what Hart used. Gas migration. Nobody wants this in their well, but in Pennsylvania, northeast Pennsylvania, 80% of the wells that have been tested prior to or post-drilling had methane gas in them. It's the most common, according to the American Water Association, Waterworks Association, it's the most common contaminant in water wells. A lot of methane gas. Some of it's biogenic, formed by bacterial action, but on the seeps, 96% is thermogenic gas, which means it's coming up from a deep reservoir. And it happens whether or not there's wells there or not. However, how to make it worse? Air drill, don't get a good cement job. Somebody leaves the valves open, leaves the tank hatches open. Yeah, then we've got more methane coming up in the air. It's operations. Regulations need to focus on that. Now, how does that fit in terms of seepage? Well, there are your big oil flows. The biggest one was not Macondo. The biggest ones was the Lakeview Gusher here in California, onshore in 1910. And they just had big lakes of oil, and they said, okay, we'll flow it in there. We'll dam up that little place down there. They flowed it with oil, and they pumped it out and sold it. And over time, yeah, the bacteria chewed up the oil. It only took, what, 50, 60, 70 years. But you read the rest of these things, most of it is either from transport or losing control of a drilling well. That's what Macondo was. When somebody switched out a mud system for saltwater, and that one still kind of bites me. Didn't have anything to do with it, but it just irritates me. Okay, but you don't see it from producing wells if you've got a good cement sheath. Even if you don't, things work in your favor. Now, here are two wells exactly alike except for one thing. One of them is a good well completion, and one of them is one of the worst things I've ever seen happen, and I did see it happen. Can you see the difference? Top of the cement in this one does not cover these high pressure, low productivity, but high pressure shales or the saltwater zone here, and this one would build up pressure. These things would gradually seep out. It would build up pressures of almost 2,000 psi at the surface. That's going to get into people's water supplies. Where were they doing this? Up in Pennsylvania. They were cementing the bottom 500 foot of casing and calling it good. That's what they changed when they changed the regulations. And basically they have to cement it, cover everything now. Good cement, multiple barriers. That's the way you build a well that doesn't leak. And we've got several that are 100 years old. Still good, tight wells. The advantage here, I'm going to go back to this one, is that from the first day you produce a well, unless you've got something leaking from the outside in, the pressure is being continually decreased in this well. And so, yeah, you may have a leak, but it'll probably be a leak from the outside leaking in. That we can handle because we can figure out where it is and plug it. You still need that good cement job. Now, this is a study. This is I broke this down. This is just the U.S. wells, 330,000 of these things. And you see barrier failure and integrity failure. Wells are made with multiple nested barriers. If one leaks and the other one catches it, that's a barrier failure, but it's not a leak. And certain experts in the field, namely Yoko Ono, have come out and said that 60% of the wells leak or 6% leak. I'm sorry, I didn't listen very much when she was talking. But basically what she was confusing was, in the Gulf of Mexico, up to 30%, maybe 40% of those wells have one barrier leaking. The next barrier catches it. Well, what is that? That isn't cement. That's connection failures. What have they done since that time? Come up with a whole lot better threads and torque turn requirements on there. Again, some regulation aspects of this thing. Now, notice the top one up here, Texas horizontal wells in the Barnett, with the exception of a couple of wells that may or may not leak, still isn't proven. Most of those, no subsurface leaks reported or found. Now, there's been some surface leaks of bad valves, of bad things in there. I'm finishing up here. Now, failure recognized here, there's several things that contribute to a failure. I want to point your attention to the second one, the maintenance culture in the company. Again, good point for regulations. Earthquakes, fracks don't really cause earthquakes, but injection wells can. Have about 20 of them in the U.S. that have initiated problems in certain areas, 20 out of 150,000. But those wells are in the wrong place. Now, red flags to the community. This is what people get into. Trucking, congestion, chemicals. Most of this can be handled if you just work with people ahead of time. Areas that have good infrastructure typically don't have that much trouble. And for as far as regulations go, this is what I look at. And those I've pretty well covered as we go on through here. There are development encouragers and there are development preventers. I'm on this side. And some of the questions I would ask, and there's a list of 25 that'll be on my website pretty quickly here. These are just a sampling of the ones that I would ask. So major risk, moderate risk, and minor risk. Kind of see where it is there. The major risk is lack of effective maintenance, lack of effective construction. There again, regulations will control that if you got the inspectors, a well-funded department, and understanding in there. That can really help what we're going on. The rest of this can be handled relatively easily. But should every well be fractured? Absolutely not. There's several areas of the world and of the U.S. that I wouldn't mess with. So those are my rules of thumb. I pretty well covered those as we've gone off through there, and I've got some things like that pop-off or pressure relief valve that are really good to kick this thing in. You want to go to the questions now? Okay, and this is a site. I will go one more. This is what the site looked like. Oops, excuse me. And that's what it looks like today. You can reclaim sites. It should be done very quickly after drilling ceases. Yes?
Okay, I'm going to explain because I
Okay,
didn't do
all right.
that at the beginning. So I forgot to explain the format, but I think we're all a bunch of smart people in this room, and we figured out that the cards were for us to write questions on, and if not, don't worry about it, you still have time. I'm going to start us off with a few questions that were submitted beforehand. So if, while George is answering these, you want to write your questions down and pass them to Garrett and Teresa, they will bring them up to me, and then I'll kind of sort them out by category if we have some similar questions and stuff, and try to get the most area covered so that George can address everything. And of course, as always, if we happen to run out of time and you still have a question, you can talk to him after, you can email him. He's got everything on his website. This presentation, if you would like it, you can give me your email address. I think George is we're going to post it on our website as well as it'll be on his website.
My website's down at the bottom here. It's just gekengineering.com.
This has also been videotaped, so for those of your friends and colleagues who weren't able to attend, it'll be posted on our website as all of our programs are in a few days, and they can watch it there. So let's see, anything else I'm missing? I think that's it. So let me get out of the way here. Is this mic on too? So I can stand on the side? I don't know. Yeah, it works. Okay, perfect. I'll just move out of the way so that if you need to tab through slides. Okay. The first question that I'd like to ask that was submitted beforehand. So California is in an extreme drought currently. It was just officially declared by the governor. And we know that fracking uses a lot of water, and much more than traditional drilling and production. Once used for fracking, I mean, we touched on this, but it was a lot of information, so you can refresh our memory if I forget. Is it too polluted to reuse without expensive processing? I think we said you can recycle water. But where do we get enough water to frack the Monterey and other prospective formations in the West?
Okay. We have drilled and fracked with treated sewage, water, effluent that would normally be dumped into a river. We have drilled and fracked with seawater. We have drilled and fracked with clean salt water that is not suitable for RO use, which is typically that which is about more than about 25 to 30,000, about seawater level. And those are the things that we can do. You can recycle any of this water. We don't care how salty it is. You can recycle. The big holdup was getting chemicals to work in high salt water. We can do that. We just have to keep the salt level constant. You do not need fresh water. Okay?
The next question I have is, what level of oil and gas production from fracking would be required for the U.S. to become a net exporter of energy? And if that happens, what is the likely impact on the U.S. and the global economy?
I was expecting difficult questions. basically, we will probably never be a competitor on the worldwide market, because to do that, you would have to compete with Bahrain and Qatar, who can produce gas for 50 cents an MCF in huge quantities. We can't hardly make it economic at $3.50 an MCF. So the odds of us getting it down that low are extremely small. I don't expect that one to fly. We will export a little bit to nearby countries, et cetera, or maybe up and down the coasts. I don't expect us to export that. I do not ever expect us to export oil. Personally, I don't think, unless Monterey comes on tremendously different than other areas, the amount of oil we get out of these shales will be significant, but not to the point of really being able to export oil. I just have no favor to do that at all. And honestly, if we're looking for energy, I think that there's a lot better places to find energy than continuing to burn oil. That's just me. Okay? All right?
Okay. Next question. From a worldwide perspective, which localities seem to have the best ways to regulate and monitor well construction and operation? And a follow-up to that is, why aren't we copying them?
Okay, the best in the world at it are the Norwegians. Okay, they and most countries copy the Norwegian regulations for offshore. They have an excellent set. We've operated under those conditions. It's fine, but they are very strict about what they do, and I have no objection to that. So that's an easy one. Now, in terms of the states within the United States, the Stronger Organization, which is an acronym to which I cannot remember the name, but it's a group of state regulators that go from state to state looking at the regulations of a particular state. Prior to 2008, 2009, the western states all had tougher regulations than anything in the east. The east has come up now. They've got some tough regulations. Some of them make sense, some of them don't, but that's okay. And now I think we're getting to a point of parity between the states of it's very, very similar, but I don't push for federal regulation. BLM is trying to do it, but I hope they default to the states, because the states know the local formations and the infrastructure much better than the feds do. And that's personal opinion again. That's not a corporate deal. That's just me. Okay?
So a follow-up to that question would be, so I've noticed, and I think we all have that, the problem, or one of the problems with state regulations is that they tend to fight each other to attract business, and it starts to become like a war to the bottom of who can, appease the companies the most. And I feel like that tends to negatively affect regulations. What are your thoughts on that?
I think that's more of a manufacturing concern than an oil and gas concern, because not everybody has the same oil and gas, and transportation comes in a lot on that. And so there are variables there that I think will cancel out a lot of that need to lower regulations. I hope no state does it.
I thought that's what happened with Pennsylvania and West
Pennsylvania
Virginia.
had poor regulations from the time of the first well onward. You didn't have to report production. You didn't have to do hardly anything. And that's why they have a mess today. So I think good regulations are an absolute necessity.
Are there many out there like you who that good regulations are necessary, and are you able to come together as a group to help influence the policy on that?
Rule by committee.
Well, like all the some of the environmentalists just want to ban it completely, and we have, in my opinion,
the world needs energy, and unless we come up with a suitable alternate energy that will work over a wide area and for a wide space, I think we're going to need every energy mix that we have in the United States to make this work. Coal's got to get cleaner. Gas and oil's got to get cleaner. Some of the alternate energies have to get a whole lot more efficient. Everybody's got something to work on. I don't think there's any shortage of work. But there are alternate energies that are sporadic. You know, they're good during the day or when the wind blows or when the sun shines, something of this nature. Oil and gas, not oil so much as an energy, electrical, but natural gas, coal, etc. Those are relatively constant, so there's a blend there. Plus, you've got the limitations of the U.S. grid, the energy grid. And if you want a nightmare, look at that one. This is going to take probably on the order of hundreds of billions of dollars to get a grid that will accept and can use multi-feed-in point source energies rather than single point sources the way it was designed. So that's going to be a tough part. I'm not sure I answered the whole thing.
I think I was trying to say that it sounds like you have a lot of good ideas based on your experience on regulations.
I haven't had many rocks thrown at me inside the industry or out, so I'm kind of a middle of the road, but more people than you realize will get behind the effective limitations. We still have a couple of companies fighting it. We still have some in Houston that we literally had to fight to get Texas regulations tightened up this last time around. With frac focus and things of that nature, there were companies just absolutely fighting us. But the majority of the companies were behind us. So I think that there is a groundswell behind it, even in the industry.
That's good to hear. So another question. After the operational phase of recovery, are there long-term stewardship duties that public stakeholders should encourage to help assure protection of not only shallow groundwater resources, but other infrastructure and resources around?
Well, that's
wells?
a no-brainer. That's a yes. And it's that maintenance culture, the culture of maintenance that a company has to take care of the equipment it has. A lot of the problems that we have and that the environmentalists point to on wells that are 25, 30 years old during the time when oil was going like this, and every time it'd go like this, they'd hire everybody with a pulse. When it went like that, they'd lay everybody off and cut all their maintenance. And 18 months later, we had to rebuild the entire field because everything was leaking. And so it's a consistent culture of maintenance. It's what we absolutely have to have.
Is that happening?
Yes, I think it is. Well, and it's happening because of Macondo. Everybody is running scared right now because they don't want to be the next one in the headlines. I mean, if I could ask a question, before tonight, how many of you had actually heard of Apache? About, okay, 20% or so. Apache's name does not get in the news very often because we try very hard to keep it out of it. Because if the media reports on an oil and gas company, it's usually bad. And that's the way we look at it.
Okay, here's a question in the realm of property rights.
Mm-hmm.
For those of us who own mineral rights, how are they protected in the era of horizontal drilling?
Every well still has to be within the boundary, and there is a setback that accounts for hydraulic fracturing. Now, if I were a mineral owner, and I have been in the past, I would look at, okay, this guy's drilling a well, how much fluid is he pumping, how long is that frac going, what's the model say? And I'd be looking at that because, yeah, you can create a frac in conventional reservoirs that might be 1,000 feet or more long. Well, the setback from your land to the boundary on your land to that wellhead might be 250, 500 feet or something of this nature. Is that taken into account? Or is he fracking under my land and draining it all? So that's an issue that's really, really spiny. I don't know how to handle that one, but I know what I'd do. I'd be looking at, how big a frac are you pumping?
What are your thoughts about the Monterey Shale here in California? Is it a safe spot to drill and operate injection wells considering the nearby fault lines?
I have no idea.
Okay, sorry.
I don't work in California. Company's not going to work here. I have no idea.
Do
I'm
you,
just
do you have
talking
any
about fracturing.
counterparts you might be able to refer us to? Or colleagues?
I don't know anybody that works out here. I really don't. How's that for a safe answer?
What aspect of the fracking debate has the biggest gulf between facts used by the two sides?
I think it's groundwater contamination by fracturing because it simply isn't going to happen. Now, groundwater contamination from spilling a load of fuel, that could happen. Well, so could an asteroid. But we hope, you've got to rank these risks, and that's what I've been doing for the last couple of years, is I've been looking at fracturing risk, and I've got a paper on that. I've been looking at well construction risk. I have a paper on that. We're going to bring one out here pretty quickly that looks at plug and abandonment risks and what are the risks there. And slowly we're working our way through how do we make this thing better.
You just mentioned plugging and abandoning wells, so I'm going to ask a question about aging wells. What will happen to them? Will they corrode and break down and leave various zones connected? And, obviously, what's the proper way to avoid problems from aging wells?
Most states have a similar plug and abandonment rule in which they're setting plugs of cement. Every plug has to be pressure tested and physically tagged in the state of Texas. That's the only one I know for sure. Those, and we've gone back and looked at wells. I don't know of many that have leaked. There's a couple that seeped, and boy, when they do, it's a real bear to try to get in there and get it fixed. So it's one of those things that do it the first time, even if you have to pay extra. You don't want to go back into one of those things. The numbers of wells that might leak, the percentages are extremely low. Two things help you. One is the plug and abandonment process. The other is you have severely decreased pressure in that particular area, and the fluids in the water column, the saltwater column on the outside, are much higher than your pressures on the well. Your leak will probably be in, and when you get a full column of fluid, it will kill that depleted zone. That helps us. Okay?
When a well is plugged and abandoned, does the casing and all the metal pipe, everything that was used in it, do you leave it there or do they take that back out?
That's state to state regulations. In Pennsylvania, they let them pull most of it back out. In Texas, you have to leave most of that there unless you're willing to mill it out and then overdress it, make a bigger hole and then get a full cement column in those areas. That's pretty expensive, so most people leave it in place. But they will remove the inner steel equipment unless it is somehow limited by natural radioactivity, which we don't have much of that in the U.S. Most of that problem is in the North Sea, but there is a little bit of it here. Southern New York, Northeast Pennsylvania, Louisiana Gulf Coast are your big ones there. Okay.
And so, so the point is to leave it in there to avoid any...
You don't pull it out of the well.
Yeah, okay.
The big thing is get it cemented right when you build the well. You have very little problems after that.
So back to the chemicals. Knowing the practical limitations of the US EPA, I am not at all reassured to know that fracking chemicals may be quote unquote approved by the EPA. Many chemicals are classified as hazardous by the EPA after only decades of widespread use. What incentive does a company have to use EPA-approved chemicals?
Well, they are at least less toxic than the known problems. And basically the way we look at that is we're using the cleanest chemicals that we know how to use right now. The Norwegians and the European North Sea have been studying this since they started drilling in the North Sea. So they have about a 20-year head start on us. And we generally check our chemicals versus what they're using. And that's the gold band chemicals are those that you can pump in the well, pull back out, and release into the ocean without disturbing the fisheries. And they have, like I say, 20, 30 years of studies on that. So you can find chemicals that have a good history behind them.
Why do you think the U.S. is so far ahead in fracking than the rest of the world? Well, I guess except Norwegians, but what are other prospects outside the U.S.
Well, we know a lot more about fracturing than the Norwegians do. Norwegians are experts on well construction.
Okay, got it.
Basically, we have done more fracks than anywhere else in the world. There's been about 2.5 million throughout the world outside of Russia. We've done about 2 million of them here in the U.S. So we've just done more than that. There's more frack units here. There is a lot more technology that has been developed here than have been developed overseas. And the big thing that makes the American oil system go is private ownership of mineral rights. Because if it's a community ownership or a government ownership, like it is in parts of Europe, there's no incentive for a surface operator to allow any drilling. So it's a kind of a political deal that it gets into there.
You mentioned that the methane contamination in water wells in Pennsylvania was inevitable due to the seepage, regardless whether or not there was fracturing or well drilling. That being said, can the natural contamination alone account for the extent of the methane concentration we've seen, or is it really just due to the poor regulation and is Pennsylvania a hotbed?
Well, that many old wells, when you start producing, and like I say, I was in a helicopter flying up and down the valleys of Pennsylvania, wondering, how in the world do I get a frack fleet in there? And then when I started talking to the operators there, and they could flow their frack fluid clear back into the river. This is 2008. And I went back and told the CEO, I said, we really don't want to be in there. And I think that companies that are in there they've heard the same things. There are several companies that are doing it right. There's a few companies that are now out of business there, which, I'm very thankful they're out of business because they were not doing it right and creating a lot of problems. But when you have that many uncharted, unplugged wells that were not built right correctly, you've got problems anytime you drill. And it's very, very hard to stop something from happening. And if something does happen, how in the world do you prove it wasn't your fault? Notice that I didn't say that somebody proves it was your fault. That isn't necessary anymore in the oil patch. All you have to do is prove a negative forever. And that's what we're into right now. It's kind of a tough deal. But I'm glad we don't operate there.
Do you live close to any hydrofracking wells? I would say your family, but you live within a 5-mile radius, so that would include them.
I live over the Katy gas field, which has been around since the 1930s and 40s. Many of the wells have been fractured. And I live 700 meters from the largest gas storage and recompression hub in the Southwest. I have heard their equipment one time in, I think it's 12 years now. One time I've heard them. And that was in a controlled release that they had to do. They flared, and you could hear them doing it. Now, as I say, there are ways to do it right. They do it right. They're good neighbors. All of their equipment is electrically powered. They don't have big diesel engines spouting, smoke and a bunch of noise. It's electric power. They have insulation walls. They really do a nice job of it. So it can be done right, yeah.
More on safety. What controls at the pump head and or loading of the oil gas transport are in place to prevent volatile explosive accidents?
We don't have a lot of problems with that, but there is a problem about 1 or 2 a year in the entire U.S. oil industry. Most of that is through training and a continued improvement on tanks, but we've still got a lot of old facilities out there. And you still got some people that are very hard-headed in terms of wearing their safety equipment, and this is one place that I think OSHA has done a very good job in terms of doing inspections, and they've focused in on a lot of plants. And those of you who are in business know that you just have to get one OSHA violation, and then they get pretty snoopy after that. And I think that that's actually helped.
That's good.
I used to see a lot more of them when I was a kid.
Yeah. On groundwater contaminants, this is in reference to one of your slides. Can you explain how your slide on EPA groundwater contaminants, which is from 1999, the data, is relevant when fracking only took off after 1995?
Well, I showed that slide to give you an idea of what it looked like before we started in with a huge amount of fracturing. Up to that time, and remember in 1999, we'd already done 1 million fracks in the United States, okay, and they weren't reporting damage. Since that time, in a shorter period, half the time, a little less than half the time, we've done another 1 million. So that was my point of going to the Texas data. I looked all over the EPA and they never took that survey again. So I went to the Texas data, got a lot of the same stuff, still didn't see it in the top 20. Had to get down into the, here is 1 in 10,000 or 100,000 wells that is leaking. And, to verify that, what I did is I went to the Gulf of Mexico data. And prior to Macondo was an outlier, terrible thing, but it's an outlier. From 1980 to 2009, that's 29 years, 0.00005% of the production leaked into the Gulf of Mexico. That of 1% now of the production. 0.0, it's 100,000ths of 1% actually leaked over that whole period. So that's what we look at and say, okay, that's a good way to run it. That's one of the reasons why we know it's barrier failure rather than leak failure, where you have all the barriers fail and it leaks to the outside. You just don't have much of that in a producing well. If you're going to have an accident, generally during the drilling phase or the transport. Okay?
So we talked about the method of plugging and abandoning wells. Oh, sorry. Can you also talk about the risks involved in that and how to avoid those?
The risks are minimized simply because you're at very, very, very low pressures by the time that's actually abandoned. But, and we wrestled with this, Apache had 700 old platforms in the Gulf of Mexico we recently sold, and I sleep a lot better at night because of that. But during that time, good friends with the guy that headed up our plug and abandonment, and they literally had to chase it until there were no more bubbles coming out of that well. And just think of the amount of area there. There'd be a lot of places for bubbles. They had to get those plugs so tight that there were no bubbles. So the rules since Macondo and the benefit of Macondo, and I hate to say there was a benefit from it, but the benefit from Macondo is it raised awareness, it made everybody absolutely gun shy about doing anything that wasn't 100%. And okay, if you got to have a downside, that's a good downside.
So one last question, and then we'd like your takeaway thoughts on the whole deal. Since a good cement job seems to be pretty key to protecting the surrounding environment, leaks and contaminations, how do you assure that it's a good cement job? What needs to happen? Okay,
there's a lot of testing that goes in. When you drill a well, you drill it, of course, from the top down, and you drill it's designed from the bottom up. Wells are designed from the bottom to the top and from the inside to out, but they're drilled from the top to the bottom and from the outside in. Okay, so you drill a 36-inch hole at the surface that goes down to bedrock, and then you drill out of that a 24-inch hole. I'm talking about a big deep well here. And you might drill a 24-inch hole down to 100 feet below fresh water, and you get a good low permeability zone, you cement that completely. So there's 2 barriers. Then you come out and you drill your first string of production casing, you cement that. That's 3 barriers. And you keep going on down through here. So every time you stop and you cement a string, you have to pressure test it in the upper zone. Some companies pressure test every zone. That's how you do it, is with a pressure test. You can run a cement bond log, and for those of you who think that a cement bond log cures everything, please go to my website. I have a paper out there which will raise a few doubts. It is a good tool. I think it's overused, and sometimes it takes a witch doctor to translate it. But there are some better ways to do it. We cover those.
So your last thoughts on what we should take away from
Well,
today?
my last thought will be kind of what I opened up with. Do it right or get out.
Thank you, George.